Thank you. I'd like to start off by thanking both Julie Robinson and AAS for inviting me to come here and tell you about the Materials International Space Station Experiment, or MISSE. And it's a real honor to present some of the results and benefits because it's a very large team. So as an outline, I'm going to give an introduction to the LEO space environment. I'll provide some examples of spacecraft damage from different spacecraft, such as LDEF Space Station and Hubble Space Telescope. I'll introduce MISSE. I'll talk about Glenn's MISSE experiments, concentrating on one of those experiments. And then I'd also like to give a very quick overview of some of the experiments from some of the other MISSE investigators. So for those who may not be familiar, materials on the outside of spacecraft are exposed to many environmental threats that can be very harmful to the spacecraft and its operation. These include solar radiation, charged particle radiation, thermal cycling, micrometeorite debris impacts, and atomic oxygen. Well, atomic oxygen is a predominant species in the low Earth orbit environment. It's formed by photodissociation of molecular oxygen by energetic UV radiation. The average impact energy at RAM velocities is 4.5 eV, and that's energetic enough to cause bond breakage in many materials. And for polymer materials and some of the other materials, the oxidation products with atomic oxygen are gases, and so the materials can literally erode away over time. And that could be a serious structural problem for spacecraft. And as one example, I've shown here that a capped-on insulating blanket, shown in the gold picture in the center on the bottom, was flown on LDEF, which is flown for 5.8 years in the low Earth orbit space environment. And that capped-on layer was completely eroded away over time due to atomic oxygen erosion. Some other examples of space environmental degradation that occurred on LDEF included structural degradation, radiation-induced darkening, and also debris generation. Materials that are susceptible to atomic oxygen erosion often will have a protective coating or atomic oxygen durable coating. But even materials with these durable coatings can degrade due to atomic oxygen erosion through a process we call atomic oxygen undercutting, where the atomic oxygen can interact and oxidize the underlying material at defect sites in the coating. And this slide provides an example of atomic oxygen undercutting erosion of a double aluminized capped-on material that was flown on space station for only 1 year. The Hubble Space Telescope provides a very good example of radiation and thermal cycling induced damage to spacecraft materials. This is a picture of Hubble taken during the last servicing mission, which was a 5th servicing mission, but they call it SM4. That occurred in May 2009 after 19 years of space exposure. Hubble has 2 materials that are outside the telescope, radiator surfaces and multi-layer insulation blankets that passively control temperatures on orbit. These materials utilize Teflon FEP as the outermost layer, and they're metallized on the back surface to provide a reflective layer. And this is a very commonly used spacecraft thermal control material because of the very high thermal emittance and low solar absorptance. Unfortunately, though, what we're finding is that this normally very stretchy material is becoming extremely embrittled in the space environment and is cracking. There are now hundreds of cracks in the multi-layer insulation blankets on Hubble, and in some cases these cracks will curl and expose the underlying material, such as the areas I've highlighted here in the red circles. Those areas then can overheat because the underlying material is aluminum and the thermal emittance is lower, and hence it can heat up. And that can be a problem for some of the more sensitive equipment which are housed in the equipment bays. So during the last servicing mission, 2 of the equipment bays, which were covered with insulation that were degrading due to the space environment, were retrieved during an EVA by John Brentfield. Those blankets have been brought back to Earth for analyses, and new materials were placed on there to maintain those temperatures on orbit. So that provides a little bit of an overview of some of the materials damage that can occur in the space environment, and hence why MISSE is so important. So what is MISSE? MISSE is a series of materials flight experiments consisting of trays called passive experiment containers that are exposed to the space environment on the exterior of the International Space Station. And these trays are positioned usually in either a ram wake orientation or a zenith nadir orientation. And the overall objective of MISSE is to test the stability and durability of materials and devices in the space environment. MISSE is a United States program with participants from NASA, Department of Defense organizations, industry, and academia. And we've had principal investigators from both NASA and the Naval Research Laboratory. There are many participants in each of the MISSE missions, and there are too many to mention, but I've listed them here on this very busy table to give you an idea of the extent of participation and collaboration in these MISSE missions. The MISSE experiments have progressed over time from primarily passive experiments to increasingly complex active experiments with in-situ data that's telemetry down to Earth. So when we're preparing MISSE for launch, what we do is we take individual experiments in trays or as individual samples, and we attach them to these suitcase-like containers, these packs, as you can see in the upper left picture. And then we close up the pack to protect the samples during launch on the shuttle. And then an astronaut does a spacewalk and takes the suitcase out to the right location on space station and attaches it, then opens up the tray with the tray surfaces back to back, and it exposes those materials to the space environment for 1 year or more. And then a future EVA is conducted, and an astronaut then closes up the tray and brings it back down to Earth so that we can conduct post-flight analysis of our experiments. So there have been 5 MISSE missions that have successfully flown to date. The current mission is MISSE 7A and 7B, which are currently up on the Express Logistics Carrier, or ELC-2. And MISSE 7A and B are manifested to be returned during the STS-134 mission, when MISSE 8A and 8B will be launched and placed on ELC-2 after MISSE 7 is retrieved. This slide provides an overview of Glenn's materials experiments. We've been very fortunate to be able to fly experiments and samples on each of the MISSE missions, and we have actually 41 individual experiments with over 600 samples that are being flown as part of MISSE. These are both passive and active experiments, and I'd love to be able to share with you a little bit about each of these experiments, but I don't have time to do that, so I'm going to just talk about one of them. The experiment I'm going to share with you is the PEACE Polymers experiment, which PEACE stands for the Polymers Erosion and Contamination Experiment. And the objective of this experiment was to determine the atomic oxygen erosion yield, and that is the volume loss per incident oxygen atom of a very wide variety of different polymers exposed collectively to the LEO space environment for a long duration. Now, in this set of polymers, we included commonly used spacecraft materials such as Teflon and Mylar, but we also included materials that you would never use for spacecraft. And the reason we did that was so that we could determine the erosion yield dependence upon chemical composition for predictive model purposes. So this experiment, we had 41 samples that were exposed to LEO as part of MISSE 2, 38 polymers, pyrolytic graphite, and we included 2 capped NH fluence witness samples. They were flown in PEC-2 Tray 1, which received direct RAM, atomic oxygen, and solar exposure. And the majority of our polymers were in thin film form, and enough layers were stacked to last for a 3-year mission, which was 2 times the original planned mission. I would like to point out that this is a collaboration with students from Hasbury Brown School for Girls. So MISSE 1 and 2 were launched in August of 2001, and then were retrieved during the return to flight mission in July 2005, after nearly 4 years of space exposure. This chart shows our experiment tray before flight with the polymer abbreviations, and then after the 4-year space exposure on MISSE. As you can see, many of these polymers have been highly eroded by atomic oxygen. This is just one example of one of our polymers, and we flew this sample UPLEX-S. We put 11 individual samples stacked together in the flight. You can see pictures of both flight and control samples post-flight. And in this case, the atomic oxygen completely eroded through the top 2 layers and into the 3rd layer, and the 4th layer is discolored. So we have determined the erosion yield of these polymers. The data is provided here along with the polymer abbreviation, and also we conducted an extensive error analysis to determine the error in these erosion yield values. 6 of the samples are highlighted in yellow, and that's because, as you may recall me saying, we stacked enough material for a 3-year mission, but MISSE actually was MISSE 2 was up in space for 4 years, so we actually had erosion that occurred either partially or fully through all the layers for these 6 samples, and the erosion yield values are not very accurate. Fortunately, I've been able to take those same 6 polymers and fly them as part of MISSE 6 so that we are able to get more accurate data for those samples. In addition to getting erosion yield values, I've also conducted erosion morphology studies of a number of these polymer samples, and this happens to be my favorite picture. And what we've learned a lot of information about the process of atomic oxygen erosion of thin film polymers. And this is actually a capped-on sample that's still intact, but has been severely eroded, and we're looking at the back surface of it. And what I like is that you can see 2 things. You can see the cones that develop when a polymer or material is eroded under direct atomic oxygen exposure. And what we can also see is that in these cone valleys, there are actually holes. This allows atomic oxygen to get down and interact with the underlying layer. So even though your film appears to be intact, you can get atomic oxygen erosion occurring down below it. And that's very important to know when you're designing spacecraft for atomic oxygen durability. So in summary, for the Peace Polymers experiment, we did obtain erosion yield data for the 39 different polymers. We did conduct erosion morphology studies, but we also did obtain optical and thermal properties of all these different polymers. And we have conducted some ground-to-space correlation tests to get correlation data for plasma ashers, which are systems that are often used for atomic oxygen durability testing on the ground. Our flight data has allowed us to have ground-to-space correlation factors, which enable more accurate ground laboratory testing. We've developed a Glenn erosion yield predictive tool. Bruce Banks has done that based on this flight data, and we've used the predictive tool for determining the erosion yield of non-flown or new materials. And I'm currently in the process of using this flight data to write a NASA Technical Standards Handbook on atomic oxygen erosion of polymers. Last, I wanted to mention that the MISSE 2 Peace data has been very widely requested, and we know that the data has had a direct impact on material design choices on a number of different satellites, including those which are listed here.